for the opportunity to speak. I've been enjoying the conference a lot, learning a lot. I will talk about some work that I did with Ross Dempsey, who's a grad student at Princeton, and Igor Klebanov. And also I'll mention some work in progress with Ross Dempsey, Igor Klebanov, and Loki Lin, who's an undergrad at Princeton. Well, as I'm sure everybody in this conference knows, confinement in 3+1 dimensional gauge theories is an important problem whose understanding is still incomplete. And it's not for lack of progress. There's been a lot of progress in numerical lattice simulations, and also not for lack of experimental motivations. There's been a lot of new discoveries of exotic hadronic states, as we've heard last week. Confinement means area law for the Wilson loop in the fundamental representation, or a linear quark-antiquark potential at large separations. The alternative to confinement is screening of external probe quarks, and this means perimeter law for the Wilson loops. In this talk, I will talk about two-dimensional non-abelian gauge theories. There was a related talk a week ago by Jaume. And the reason to focus on 2D for these questions about confinement and screening is that it's simpler, and it's simpler because the gluons in 2 dimensions are not dynamical. So the simplest 2D gauge theory one can consider is just pure SUN non-abelian, pure SUN gauge theory, which is confining. The Coulomb potential in 1+1 dimension grows linearly with the distance. The fundamental string tension is proportional to g squared times n, and the theory has no particles, so it's pretty simple. A slightly more complicated theory would be the Tuft model, where one combines the SUN gauge theory and adds to it one fundamental Dirac fermion or quark of some mass m fundamental. And this theory is a little more complicated. It's got the particles. The particles are mesons made of quark and the antiquark. And at large n, the spectrum of this particle, of this theory, was solved by Tuft in the 70s using light cone quantization. The spectrum is discrete, and there's just one rigid trajectory. Maybe the Tuft model is still a bit too simple because it lacks adjoint degrees of freedom, dynamical adjoint degrees of freedom. So then the more complicated theory that was considered starting in the 90s was SUN gauge theory with one adjoint Majorana fermion, which I'll refer to from now on as a gluino of some mass, M adjoint. This theory was studied at large N using discretized light cone quantization, DLCQ, in the 90s. Or more recently using light cone Hamiltonian truncation. So one interesting thing about this theory is that when the mass of the adjoint is 0, then the theory still has a mass gap, and it is screening, even though it doesn't have any degrees of freedom in the fundamental, dynamical degrees of freedom in the fundamental representation. Well, I mean, I should say that, as was pointed out in some of these papers, one might have to do some additional tuning of some interactions in order to get to the screening case. But nevertheless, I mean, it's still, I think it's still very surprising in some ways that this theory with this theory without any fundamental quarks is screening. In the deep infrared, this theory is described by a coset model. This is the coset with the vanishing central charge. If one then turns on the mass for the adjoint Majorana fermion, then the theory still has a mass gap. The masses just change a little bit if we turn on a small mass, but the theory is now confining. The particles in this theory are what I'll call gluinoballs. So they're just made of the Majorana fermion. Another feature of this theory is that it's got discrete theta vacua, as pointed out by Witten a while ago. What will I do in this talk? I will talk about the next more complicated theory, which is SUN gauge theory with the adjoint Majorana fermion, the gluino. And I'll set for the rest of this talk, I'll set its mass to 0. And to that, I will add a fundamental Dirac fermion of some mass m fundamental. So the Lagrangian for this theory is this, the gauge part. There's the gluino part, the adjoint Majorana part, and the fundamental Dirac fermion. And the primary interest in this talk would be to consider the fundamental to have a non-zero mass, and in particular, to have a large mass, in which case we can think of this quark as being a probe of adjoint QCD. So by probing adjoint QCD with a fundamental quark, maybe we'll be able to learn more about this screening versus confinement question. So I'll work mostly, except for the last slide, in the limit when n goes to infinity. And in this limit, the flux tube breaking is suppressed in 1 over n, so one doesn't have to worry about that. And I will study this theory, the SUN gauge theory, with one adjoint Majorana and one fundamental Dirac fermion in light cone quantization, as was done in the 90s with adjoint QCD. So briefly, how that works is that we can think of the light cone coordinates x plus minus that are t plus minus x over square root of 2. We can think of x plus as time, x minus as space, and just perform canonical quantization. So in this diagram, these 45-degree lines are the space direction, and time runs in this direction. And the massive particles in this theory and the right-moving massless particles intersect the time slices, so they can be captured in light cone quantization, but the left-moving massless particles cannot. However, this will not be an issue for us, so just look at the massive spectrum. The way light cone quantization works is that we have light cone momenta, p plus and p minus. They commute, so they're simultaneously diagonalizable. And in order to find the massive spectrum, we should find the eigenvalues of this operator m squared, which is 2p plus p minus. So if we simultaneously diagonalize p plus and p minus, then we'll also have m squared be diagonal. Okay, so how does it work in this theory in a few more details? Well, you can choose a gauge where a minus is 0, and then write the fundamental quark Q and the adjoint is the 2 component spinners. And then notice, if we write out the Lagrangian, notice that A plus, as well as half of the components of the fermions, namely phi and chi, are not dynamical, and they can be eliminated. So the only dynamical fields are this V and this psi, and then one can just expand them in modes, and the coefficients are just creation annihilation operators. Now, in order to study the problem numerically, one should do some discretization. So the approach, and goes back to this paper, is to compactify the x minus direction, this is a spatial direction, into a circle of radius L, and impose anti-periodic boundary conditions for the fermions. Here I wrote down the expansions of psi and V in terms of modes. Anti-periodic means that the momenta are in odd integer units of 1 over 2L. So we have n over 2L is the momentum, and this B and B dagger, D and C dagger, as well as the conjugates D dagger and C, are just the creation annihilation operators. B and B dagger for the adjoint, C, the C dagger, D dagger for the fundamental. And then one can construct the states at large n. There are various single trace sectors and multi-trace sectors that don't mix. The single trace sector consists of gluinoballs. So these are just gauge invariant operators obtained from acting with a number of B daggers on the vacuum. And then we also have mesons, where we start with a C dagger, then we have a chain of B daggers, and then a D dagger with adjacent indices contracted. And of course, there's also multi-trace states. Now, the spectrum of gluinoballs is exactly the same as the spectrum of gluinoballs in hadron QCD without the fundamental. What's new in this theory is that we can also look at the mesons. So to figure out the spectrum, we can, the way to do it is just fix the value of the momentum. So these numbers here, n, so that the momentum is n over 2L for each quantum. So n is odd. We just fix their sum to some value k, which is an integer, and then write all the states. For fixed k, there's finitely many states with this value. And then depending on whether we chose k to be even integer or odd integer, we have either bosonic states or fermionic states. And then in this basis for a fixed k, we can write p minus the light cone Hamiltonian as a finite dimensional matrix, then diagonalize it, and from that we can extract the eigenvalues of m squared. This k is a resolution parameter. The idea would be to send it to infinity, and then we obtain the masses in the continuum limit. So I want to show you some results, both for gluinoballs, proving on what was done in the 90s, and also for mesons. Before I do that, only one small comment, which is that there's a charge conjugation symmetry in this model. That will split all the states, bosons and fermions, into charge conjugation even and odd. So I'll call them Z2 even and Z2 odd. So these are numerical results for gluinoballs. So as I said, the first time was done in the 90s. And so these are the masses in units of g squared n over pi as a function of 1 over k. Sending k to infinity means we just look at where these lines intersect the y-axis. So what we see here is that the lowest particle is some particle with mass 5.72 in these units, and then there's some other states over here. And as I'll say, what this looks like is like a continuum starting at 22.91, which is about 4 times 5.72. This is...
Excuse me, may I ask a question? Does this 572 depends on the value of the fundamental mass, or you fix this parameter?
The fundamental mass, this is for gluinoballs, and the fundamentals don't affect the spectrum of gluinoballs, so it does not depend on it.
At large N. And what about if you put fundamental mass equal to 0? Even this is unimportant.
One can do that, and then one has massless meson states, but this doesn't affect the gluinoball spectrum.
Okay, thank you.
So this is the Z2 odd spectrum, and again, so there's some state here, 17.19, and then it looks like there's a continuum starting over here, and there's a continuum in each sector. So then there's the bosons, Z2 even, where one state over here, and a continuum, and also for Z2 odd bosons, a continuum. There's no states below the continuum. I should say that this continuum the existence of this continuum is very surprising. I mean, these are single trace states, so one would not expect a continuum in this sector. Okay, so now in these plots, as you might have noticed, some of the points here were black and some of them were orange. So now I want to explain why I colored them in this way. I mean, they're all states. So I want to explain why there's a difference in color in the plots. The difference comes from the fact that there are some exact degeneracies in this discretized problem that were noticed in the 90s. The degeneracies are as follows. So if we compute the eigenvalues of P minus for some values of K, and then we add them together, these eigenvalues of P minus, we obtain another eigenvalue of P minus, the value of K that's the sum of the Ki's where we computed these eigenvalues of P minus. And this works only if these eigenvalues of P minus are for fermionic gluinoballs. That's a curious relation. And orange points in these plots obey this exact relation. So for instance, all these orange points over here are sums of two P minus eigenvalues at lower values of K. And in the fermions, the plots for fermions, these orange points are sums of three P minus eigenvalues at smaller values of K. So it's a curious relation. The question is, why do we, what can we get out of it? Why do we care about it? And the other question is, what's the explanation for it? So why is this important? It's important because it shows, so this relation, if you think about what this means in terms of the masses, it's a couple line proof that if you have such a relation, then for any set of fermionic trajectories that asymptote to some masses mi as K goes to infinity, there would be a continuum starting at the sum of those masses. It would be in the fermionic or bosonic spectrum, depending on whether we add together an odd or an even number of masses. So observing such a relation, from that one can prove that there should be a continuum. Of course, this is only when the mass of the adjoint is zero. When the mass of the adjoint is bigger than zero, the continuum completely disappears. So next, I want to explain very briefly.
May I ask you at this point, so that refers to the theory with fundamental fermions, and for pure adjoint theory, are there these degeneracies where what happens?
Yes, so the spectrum of gluinoballs doesn't care about the fundamentals, so this happens for the pure adjoint theory too.
But you said that it depends on the mass of the adjoint fermion, and the spectrum of gluinoballs, well, I believe shouldn't depend too much on the spectrum of adjoint fermion.
It depends on the mass of the adjoint, but not the mass of the fundamental.
Yes, yes, but you said that this degeneracy which you observed is only for adjoint masses equal to zero, right?
Correct, yes.
And so why it's important, the mass of adjoint fermion for pure adjoint theory?
No, but it is a gluinable, so they made out of this adjoint fermions.
Yes, yes, I understand, but
yeah. But there's no other glue balls.
Yes, yes, but it's not a story about screening versus confinement, because
not yet. There would be a story about screening versus confinement when we look at the mesons.
Yes.
So I'll show you something similar for mesons.
Well, okay. So, well, I continue, please. Probably.
Yeah. But what I wanted to do was to first explain why this happens for the gluinoballs, and then we can just look at the mesons afterwards.
Okay.
But Silviu, would you say it's a large N disease?
This is what happens with large N. Yeah, that's correct. It's a large N. These degeneracies, as I'll explain.
Well, the number of colors, incidentally, how large is N in your calculation?
N is taken to infinity. This is a large N limit.
Large N limit. Okay.
Large N limit, and these are the single trace states. Yeah.
Okay.
Yeah. So the explanation for these degeneracies comes from, there's two parts to it. One is some universality property of the massive spectrum that was noticed by Kutesov and Schwimmer. And then there's also large N factorization. So let me explain briefly. So if we take 2D QCD with massless fermion in any representation, then and work out what P minus is, it can be written just only in terms of the modes of the SUN current. These J of N are just the modes of the SUN current. The SUN current obeys a Kac-Moody algebra at some level, Km. Commutation relation is given by this. Kkm appears in the commutation relation. Now, if you think about the states split into representations of this Kac-Moody algebra. each representation starts with a primary that's annihilated by all the modes of J with n bigger than 0 with positive frequency. And then we have descendants obtained by acting with a J's with negative frequency on the primary. Of course, this is all the states, gauge invariant and non-gauge invariant. Now, from each representation, we should select only the gauge invariant ones, which are the ones that are annihilated by the 0 mode, which is the charge. The fact that P minus only depends on J means that the P minus eigenvalues only depend on, we can compute them by just, if we act with P minus on these states, you just have to commute some J's around, and the only thing they're going to depend on is the level of the Kac-Moody algebra. So the eigenvalues of P minus depend on the level as well as the precise representation of the Kac-Moody algebra that one is looking at. What this implies is that if we have two or more Kac-Moody primaries or representations, representations are given by a Kac-Moody primary in a given representation of SUN. So if we have two or more Kac-Moody primaries in the same representation of SUN, in the same theory or in different theories that have the same value of the same level for the Kac-Moody algebra, then we have the same P minus eigenvalues. So now we can apply this to the following situation, and then we'll be able to explain the degeneracies. So for massless adjoint QCD, now ignoring the massive fundamental fermion, the Kac-Moody level is n. We can have another theory with the same Kac-Moody level, which is QCD2, SUN gauge theory with n fundamental quarks. So we replace the massless fundamental quarks. We replace the massless adjoint with n massless fundamentals. So these two theories share the same part of the same spectrum, the same eigenvalues for P minus, and then we can try to understand how the states in one theory map to the states in the other theory. So in the first theory, the simplest thing we can do is to construct gauge invariant states. We can act on the vacuum with a trace of various J's. And this is the same as what we can do in this other theory in the blue one. And this gives some bosonic gluinoballs. The next thing we can do is to act with a bunch of J's as well as a B dagger of 1 and take the trace of that. So this would give some fermionic gluinoballs because we have an extra B dagger. And if we think about, I mean, I'm not explaining, it's not entirely obvious that this is the case, but this is the result, that in the other theory, the states that have the same eigenvalue for P minus look like this. There's a C dagger of 1 with just 1 unit, and then a bunch of J's, and then a D dagger of 1. So I call this with all adjacent indices contracted. So I will call that single string states. And then we have states which in one theory have 2 B dagger of 1s. And these states in the other theory would look like 2 string states made out of 2 strings. So we have a C dagger, a bunch of J's, a D dagger, and then another C dagger, a bunch of J's, and another D dagger. And because in this other theory, these states are 2 string states, this theory also obeys some version of large N factorizations and one can show that the P minus eigenvalues of such states are just sums of P minus eigenvalues of these single string states. So,
can I ask a question?
Yeah, sure.
So these two theories, massless adjoint QCD and massless 2D QCD with fundamentals, have completely different global symmetries.
That's
so
true.
How can I think about this identity in light of that, including for massive states, because they would be fitting into irrefs of completely different global symmetries,
yeah.
For example?
Well, so there are some states that have some P minus eigenvalues in the first theory, and in the second theory, there's some other states that have the same P minus eigenvalues. It doesn't mean that all the massive states from one theory correspond to massive states in the second theory.
It is kinematical, essentially.
It is essentially kinematical, yeah. Well, I mean, yeah. Yes, it depends on. It relies on the fact that P minus can be written just into the current.
Mm-hmm.
But there's no equivalence of the two theories. We don't know. We just know that the P minus eigenvalues for a given Kac-Moody representation are the same. but we don't know the multiplicity of the representation. So that's what
I see
in the various theories.
But somehow one wants to use this to argue for deconfinement, and in the blue theory, the fundamental QCD, I mean, there's no center symmetry anyway, so it's obviously deconfined.
Yeah, I'll explain how.
But the global symmetry is different anyway. So okay, go ahead.
I'll explain how that comes about in a bit. Yeah, and then we can have fermionic gluballs in the first theory that could look like triple string states and so on. So, at large n, this argument shows that large n, the p minus eigenvalues of n bigger than 1 states. These were the orange dots in the previous plots, are sums of p minus eigenvalues of the n equal 1 states. And the n equal 1 states are all fermionic gluballs, and that's the reason why we could add eigenvalues only of the fermionic gluballs and get eigenvalues of p minus. And so what do these arguments prove? They prove that there exists a continuum starting at 2m1 in the bosonic spectrum, for instance, where m1 is the lowest fermionic glubal. So far, might not have much. I mean, it's a curious thing. It may not have a direct connection to a confinement. So now I want to go on to mesons. So in DLCQ, can also compute the spectrum of mesons. I'll focus on the case where the fundamental mass is non-zero. And I'll set in the following plots, I'll set the fundamental mass to 1 in units of g squared n over pi. Just as an example, of course, we did it for various values of the fundamental mass. So again, for the mesons, we have Z2 even, Z2 odd, fermions, and bosons. So this is fermions, Z2 odd. It looks like this. So it looks like there might be a continuum starting around 8. Then fermions, Z2 even. Again, it looks like it might be a continuum starting around 8. Boson, Z2 odd. It looks like there's a continuum starting around 8 and also a separate state below the continuum around 6.55. And bosons, Z2 even is just a continuum starting around 8. So this is what the numerics gives. So again, in these plots, I colored some points as black, orange, and for fermions also blue. And now I want to explain what those colors mean. So as we had this correspondence of p minus eigenvalues in the two theories without the massive fundamental, now we just add a massive fundamental to this correspondence. So we have theory T, SUN gauge theory with a massless hadron and 1 massive fundamental, and theory T prime, SUN gauge theory with n massless fundamentals. I call these light quarks in this theory T prime, and 1 massive fundamental. I call this a heavy quark in theory T prime. And one can again just look at the various states in the first theory, various states in the second theory, and match the states that have the same p minus eigenvalues. And it's a similar story that the mesons in theory T look like states in T prime that look like, in general, multi-string states that start with C dagger, a bunch of J's, a D dagger, C dagger, a bunch of J's, a D dagger, and so on. The only question is whether these C dagger and D dagger correspond to the heavy quark in theory T prime or to the light quarks.
Okay.
So the simplest thing we can have.
When you say you have n massless fundamentals in a meson, do you mean it's one fundamental, one anti-fundamental, or they're both fundamentals? Because if they're both fundamentals, you cannot get a color singlet state adding any number of adjoint fields, right?
Sorry, so for the fundamentals, I mean, it's a complex fermion. So I have the creation, I have a quark and I have an anti-quark.
Okay. And then presumably you assume that it is in the adjoint color state in order to be able to make it, to whitewash it by adding some gluons, right? Because
yes, that's how it's going to work. Yes.
Okay.
Yeah.
Yeah.
Okay, good. So the simplest state that we can construct are bosonic mesons, which in theory T, and again, I'm just showing you the results. It's not obvious from what I said, but this is what we find. In theory T prime, they look like only one string of these things, starting with a heavy quark and ending with a heavy quark. And then we can have fermionic mesons in theory T, where in theory T prime, they start with a heavy quark. It's a two-string state, heavy light string, and then a light heavy string. And then we have bosonic mesons, which are like 3-string states: heavy, light, 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 heavy. And then we have fermionic mesons, which are 4-string states: heavy, light, 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 heavy, in theory T prime, and so on. So now if you look, for example, at the state over here, the M = 2 state, this has heavy, light, and light, heavy. That's exactly what the fermionic meson looks like. And a light, light string, which is like a fermionic gluinoball. So from this, one can show, and it's true, one can check that the P- eigenvalues of these M = 2 bosonic mesons are sums of P- eigenvalues of M = 1 mesons, these fermionic ones, and N = 1 gluinoballs. And same for similar story for these other ones. So this is what the colors meant in the plots. Now, what this shows is that the fermionic mesons, the M = 1 ones, in theory T, correspond to 2-string states in theory T prime. So what this means is that the P- eigenvalues of these mesons in theory T are sums of P- eigenvalues in theory T prime due to the large N factorization of theory T prime. So this proves that there's a continuous spectrum of mesons, fermionic mesons in theory T. So now, what does this mean for the question of confinement versus screening? It means that since there's a continuous spectrum of mesons, it means that the quark-antiquark potential levels off. And this implies that there's screening in the adjoint QCD theory. So the theory without a fundamental. The fundamental is just a probe of adjoint QCD. If we compute the quark-antiquark potential, then because the meson spectrum has a continuum, it means that the potential level's off. Now, as I showed you earlier, there was also a one bound state over here in the Z2 odd bosonic mesons. So this means that the potential, quark-antiquark potential, cannot be exactly flat. It's going to look like this. It's going to start with a Coulombic type behavior in 1+1 dimension, which is linear at the origin, and then it's just going to level off to some value. And above this, this is where the continuum is.
Silviu, I do not understand this argument. We know that the potential levels off even at finite n.
Okay, yeah, this is an argument for it at large n.
Yeah, but that argument doesn't mean continuum, because we know that the potential levels off at finite n.
Well, what the argument that I gave shows is that there is a continuum, and the continuum then implies the leveling off.
Okay, you're not saying that the leveling off implies a continuum.
I'm not saying that leveling off implies a continuum. I just proved that I can prove that there's a continuum, and that implies that the potential level's off.
Okay, thank you.
I have another question. And this plot at the top of your, in this figure at the top of your, yes, here, what these two little crosses, what kind of a field they denote?
Yeah, okay, so this is just an illustration of the fact that the meson in theory T corresponds to a 2-string states in theory T prime. So it essentially.
Okay, but what it is? What I mean, I understand that the fundamental quark is at the very top, but then the little cross. Little cross is, what field does it mean? Is it a quark field or a joint quark field?
Quark. It's a massless quark in theory T prime.
Okay, so it breaks. No, but you said that your quarks, fundamental quarks, are very heavy. Right, because they're probe quarks. You said that they're my probe quarks. If they are very heavy, it's one story. If they are massless, it's totally different story. Then they are not probe.
But Misha, inside it is massless quark.
Yeah.
It's massless quark.
There is blue theory and red theory.
Yeah, in theory T, in the original theory, the fundamental is massless. In theory, but the adjoint is massless. Theory T prime has we replace the massless adjoint with n massless fundamentals, and then we also have the massive fundamental.
In theory, T is just to illustrate that the heavy state, like heavy quark, can essentially be screened by a cloud of adjoints.
But then this is a
This
trivial.
illustrates.
You don't have to do all this exercise and numerical calculation in order to see that if you have n massless quarks, the string will break via pair production. It's no longer
The non-trivial statement is about theory T, that the adjoints can essentially, that when you move the heavy quarks far apart, they're screened by adjoints. That's what this illustrates.
Okay, then this figure 1 has no relevance whatsoever, right?
Yeah, in theory T prime, it's more or less trivial. In theory T, the implication for theory T is that what non-trivial.
Okay.
Yeah.
Silviu, does this analysis pass the consistency check of adding the quartics? Because once you add the quartics, the potential doesn't level off. So would you say that there is no continuum then?
Yeah, this argument does not. I don't think it goes through if you have.
We can't calculate with the quartics.
And also in DLCQ, we cannot calculate with a quartic term that.
Wait, why not? What's so hard? I mean, I understand it'd be harder, but what is it impossible?
It's impossible using the same method.
Huh.
You can't integrate out these right-handed quarks.
Yeah, integrating out the fermions is harder.
No, you still can integrate them. Probably it's more complicated, but it's
more
still
complicated. Yeah.
Yeah, it's much harder. Maybe possible.
Yeah, let's see if we'll finish because we're running short of time.
Anyway, yeah, I feel like I'm running out of time. So what I wanted to say one thing, which is that one can actually calculate exactly what this V infinity is from the DLCQ results. So one can estimate it from where the continuum starts. So when the mass of the fundamental is large, the continuum starts at twice the mass of the fundamental plus this V infinity. So of course, the mass where the continuum starts can be more accurately estimated from doing DLCQ directly in the theory T prime, which is what we did. So this is a plot of that. This is where the continuum starts as a function of on the x-axis twice the mass of the fundamental. This is a 45-degree line, and this is the solid line is where the continuum starts. So you see that it's offset a little bit, and that's exactly the value of this V infinity. We got 1.1 times square root of g squared n over pi. Of course, this is large N. I had a slide that said that, well, this method of extracting V infinity passes a consistency check. The consistency check is that we can generalize this whole thing to the theory where there's several massless adjoints. So if we have an adjoint, massless adjoints, and one massive fundamental, and then again, same kind of thing, we can extract V infinity. And this is a plot of that as a function of 1 over n adjoint. And when the number of adjoints is very large, we can do perturbation theory in 1 over the number of adjoints. And there we can just compute the expectation value of the Wilson loop analytically. First integrate out the fermions and get some effective action for the gauge field, and then compute the expectation value of the Wilson loop. And this is the value of V infinity in that case. And in this plot, the way it's plotted, that would correspond to the straight line. So the fact that this curve that we obtained matches the straight line at 1 over n adjoint going to 0 shows that this method, this is the consistency check. So I wanted to say one other thing, which is that, so we also started looking into doing DLCQ for finite n. Just a preliminary result of that, just to get an idea of what the 1 over n corrections to the various masses are. So this is, again, so the original setup where we have only one massless adjoint, and n equal 2, so number of colors is equal to 2. This is what the various states look like. There's this is both bosons and fermions. There's the lowest fermion is at 5.73. The next, the boson is 10.81, and then looks like there's a continuum starting here at 4 times the value of the fermion in the bosonic spectrum, and then there's a continuum for the fermion starting over here. And what's striking, I think, about this plot is how small the 1/n corrections are. So the mass of the lowest fermion at n equals infinity was 5.72, at n equals 2 is 5.73, and for the bosons, the mass at n equals infinity is 10.78, and at n equals 2 is 10.81. There's way fewer states here than the states for the large n, and that's the reason for that is that for an SU2 gauge group, there's various trace relations that kill some of the states. Okay, so maybe I should conclude. 2D gauge theories, hadron matter, interesting toy models. DLCQ gives a good quantitative handle on the bound state spectrum, and the continuous spectrum of mesons made of heavy probe quarks, for which one can find an argument at a large n that proves that there is such a continuum. This can be used to argue for the screening of the theory as opposed to confinement. There's various questions left for the future, and I listed here some, like a more systematic analysis of 1/n corrections, the precise quark anti-quark potential, studying non-trivial flux tube sectors with DLCQ generalized to other models, study hadron QCD on a spatial lattice, adding these 4 fermion interactions either in DLCQ or on the spatial lattice. So yeah, sorry, I probably went over time. I'm sorry about that. Thank you.
Yeah, thank you. Very nice talk. So we have lots of discussions and we did run out of time. So I suggest, unless there is one very urgent question, I suggest to postpone discussion till discussion session, which we'll have afterwards. Well, I see.
I have just one small question,
Okay.
Sergey. Small question. Well, in these issues for the future, you didn't mention studying the theory for non-zero adjoint fermion mass, because if you could do that, then you should see that confinement is restored for non-zero fermion mass, right?
Yes, that we have done. I mean that. That we can do, and indeed we see that the continuum disappears.
And can you say how the exact dependence of the string tension on the fermion mass?
From DLCQ, that's a little, we haven't been able to extract it.
You will be able to do it in future, probably, right?
That's something we have on our minds. Yes.
Okay, thank you.
But I mean, the workers of Zohar and company shows that it's linear in mass as we turn on the.
Yes, but you can check it numerically, right?
We can. So far, we cannot check it numerically. I'm not sure I know how to do it, but yeah, that's something that's on our mind. Yes.
Okay.
Okay, I see there is a very last question from Arkady.
No, maybe I'll ask later. So I am okay with it.
Okay, then let's thank Silviu.